We physicists have held up 100 years, starting around 1916, for this photo. A local dark opening may very well be one of the most captivating and baffling peculiarities in the universe. They are huge monsters with regards to gravity, yet at the same time, for all intents and purposes imperceptible to us. A dark opening weighing maybe 2 to 4 million times the mass of the Sun, however, in view of the research that was put into them over the last 2 or 3 decades, we've gone from knowing literally nothing about them to getting to find out increasingly more very close and personal. Things have recently gotten more insane. Miss Yaku recently reported that we finally got a glance at what's inside a dark opening, and this new data carries light to the subtleties the universe of science could have missed from the start. Join us as we dig further into dark openings and uncover what's inside. Space is huge and awful. What are dark openings? Before we get into the details of what Kaku found, we have to discuss the basics. Although most of us have some idea of what dark openings are, there are still a few holes in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the presence of dark openings. At that time, the concept of dark openings was absolutely hypothetical. It required an additional 50 years for the scientific community to find proof that dark openings really exist. This occurred in the 1960s when they were considering the Cygnus X-1 heavenly body and saw a strangely radiant blue star that was producing X-rays. This star was certainly not a stale object but was circumventing a giant dark something. Upon further examination, it was seen that the X-rays weren't just moving around on their own. They were being sucked into the dark thing they were circling. Hence, the name dark opening. This discovery was huge because it provided evidence that dark openings really exist and they weren't just an invention of Albert Einstein's wild imagination. While that was incredible, it also meant that there was this stunning substance in space that we urgently needed to learn about. So, scientists from one side of the planet to the other got to work. This dark opening was named Cygnus X-1, and it is located in the group of stars Cygnus, around 6,000 light-years from Earth. It was no small discovery. It's multiple times more brilliant than the Sun and unquestionably dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is known as a dark opening. The concept of a dark opening is both intriguing and frightening. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a dark opening will be pulled into it, gone forever. However, that part of danger makes it even more important to learn everything there is to know about them. Was this it? Or were we just starting? The answer turned out to be the latter. After the discovery of Cygnus X-1, researchers began to look for other dark openings. They found that there might be nearly 100 million dark openings in the Milky Way alone. But because they are so incredibly difficult to detect, we still don't have an accurate number. By all accounts, there are several million dark openings in the Milky Way, in our very own galaxy, which makes them even more important to study. So let's break it down. The main concern with dark openings is always going to be gravity. Their gravitational pull is so intense that anything that enters it packs down cosmically until it becomes a singularity. In simpler terms, dark openings are like vast vacuum cleaners that suck everything in. One of the most startling parts about the research into dark openings is the fact that if someone were to fall into one, they would reach a point where they become a singular line. This process would happen slowly, and the person would die before the final form of reality sets in. So let's just say that nobody should step into one, but they're everywhere. So could we be in danger? Despite the fact that the nearest dark opening to Earth is around 500 light-years away, it's still close enough to raise multiple concerns. In 2021, researchers were able to produce the first clear photo of a dark opening, the M87 dark opening. This dark opening was captured over several nights, and with each photo, the scientists gathered more and more proof about it. They had to line up the individual photos to fill in all the gaps. In doing so, they were able to determine that there are 3 layers to a dark opening. It's not just one single expanding hole of nothingness, as many people believe. Things are much more complicated than that. To even get to the nothingness part of a dark opening, you have to make it through the first 2 layers. The first layer is known as the event horizon, which, while in the first layer, is the point of no return. Once you pass the event horizon, pressing forward is your only real option, and you will be sucked into the dark opening. But the 3 layers just get worse from there. The second layer is the photon sphere, where light orbits the dark opening. Any light that enters this region will be caught and cannot escape due to the dark opening's gravitational force. Finally, we come to the third layer, the singularity. This is where everything that enters the dark opening is compacted down cosmically until it becomes a singularity. The singularity is a point in spacetime where the laws of physics, as we know them, break down, and we can't predict what happens next. Now, what makes all of this even worse is the fact that each dark opening you study will be entirely different from the last. Sure, they do tend to follow the same 3-layer concept, but the way they function could be vastly different. At this point, if this were anything else, all we would need to do is hop back on those telescopes and simply study the basics in detail. But with dark openings, you can't really do that. Researchers can study dark openings indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe into a dark opening is not possible because anything that enters the event horizon is pulled toward the singularity, where it is compacted into an infinitesimally small point. So, you can't exactly waste billions of dollars just to get an impression every time, because the second the probe gets close enough, it will simply be crushed into nothingness. Because of that clear issue, researchers are left with no choice but to study these objects in a 2-dimensional way, even though they are 3-dimensional singularities as a general rule. To make matters even more challenging, there are also the 2 issues of each dark opening being unique and the laws of physics, as we know them, breaking down when we try to investigate the interior of dark openings. Traditional methods of scientific inquiry don't really apply to the study of dark openings. That doesn't mean researchers haven't been busy. There are lots of different theories and explanations for dark openings, and with each one, things get more and more fascinating. One of the most compelling theories about the formation of dark openings is that they are made from collapsed stars. At that point, when a star depletes its fuel, it can no longer generate enough energy to counteract the force of gravity that is constantly pulling inward. So the star begins to implode on itself, shrinking and becoming denser as it does. If the star is massive enough, this process can continue until it turns into a singularity. To understand the concept of dark openings in depth, NASA researchers turned their attention to the center of the universe, M87. Astronomers observed a really powerful whirlpool of very hot hydrogen gas that was rotating at a shocking pace of 1.2 million miles per hour. The sheer power of the rotating gas disk should have caused it to violently fly apart in all directions. However, it didn't. Researchers discovered that there must be a titanic mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns, and it had to be a dark opening. But that's not the only theory regarding dark openings. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a rotating dark opening. He showed that a rotating dark opening wouldn't collapse into a point as previously thought, but rather into a ring of fire, or a thin disk. The disk would rotate so quickly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the ergosphere, and it's the region surrounding the dark opening where the laws of physics begin to break down. However, the most interesting feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical tunnel through spacetime that connects 2 separate regions of the universe, or even 2 parallel universes. The idea is that if one were to fall into a dark opening, instead of being crushed to oblivion, they would be sucked down a tunnel through the ring of fire and shot out a white opening into a parallel universe. To understand how this works, we need to look at the concept of spacetime. In Einstein's theory, the reality we experience isn't composed of independent entities, but is interconnected, forming a 4-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating a gravitational field that makes other objects move toward them. Now imagine a sheet of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through spacetime that connects 2 distant points instantly. Wormholes aren't just a science fiction concept. They're actually a prediction of general relativity. Although no one has ever observed one directly, the reason is that wormholes are inherently unstable and would collapse very quickly. However, the presence of an Einstein-Rosen bridge would mean that dark openings are not just vast vacuum cleaners but could also be portals to other regions of spacetime. So could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can travel through spacetime. But even so, the theory of wormholes and dark openings as pathways to other parts of the universe, or even to different times, has been a subject of interest and speculation among physicists for a long time. The idea that there may be shortcuts through the fabric of spacetime allowing travel across vast distances or even into the past could be revolutionary if we could actually achieve it. One of the most captivating ideas in this field of study is the CR wormhole, which is named after the mathematician Royer, who first described Einstein's equations of gravity. This kind of wormhole is essentially a theoretical cylinder through spacetime that could connect two distant points, such as two different universes or even two different times within the same universe. The mongrel wormhole is ring-shaped, similar to the mirror in the tale of Alice in Wonderland, and could actually move a traveler to another universe or another time, where the laws of physics might be quite different from the ones we're familiar with. But at the destination, that could just be normal. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've mentioned before, it's also a subject of debate and discussion among physicists. Some have pointed out that wormholes, and especially dog wormholes, may be unstable or difficult to cross due to the extreme radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and dark openings, only work for gravity, not the quantum forces that govern radiation and subatomic particles. To understand the true nature of these phenomena, another theory is needed that can combine the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can unify both Einstein's theory of gravity and the quantum theory. Michio Kaku, a famous theoretical physicist, has been working on a theory of everything for many years as well. While there are many versions of what this could be, the one that has shown promise is the superstring theory. Superstring theory combines gravity with the theory of radiation. The theory suggests that subatomic particles are actually tiny vibrating strings and that the universe is an ensemble of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the fascinating things about superstring theory is that as a string moves through time, it bends the fabric of space around it, creating dark openings, wormholes, and other exotic solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with the quantum theory, but it also explains many of the mysterious phenomena we see in the universe. However, there's a catch. The additional dimensions of spacetime that superstring theory requires are so small that we can't even observe them directly. As we continue to probe the nature of black holes, another essential aspect to understand is the role of Hawking radiation. Proposed by physicist Stephen Hawking in 1974, this concept suggests that black holes are not entirely black, but instead emit a faint radiation due to quantum effects near the event horizon. This radiation occurs because of the interactions between virtual particle pairs that spontaneously arise from the vacuum of space. Normally, these pairs annihilate each other quickly, but near the event horizon, one of the particles can fall into the black hole, while the other escapes into space. The escaping particle manifests as radiation, which theoretically could cause the black hole to slowly lose mass and eventually evaporate, a process referred to as black hole evaporation. Although this idea is groundbreaking, detecting Hawking radiation remains challenging, primarily because it is so weak and difficult to observe. The study of black holes also offers insight into some of the most fundamental questions of physics, especially regarding the relationship between quantum mechanics and general relativity. While general relativity effectively describes the large-scale structure of space and time, quantum mechanics governs the subatomic world. Yet, the two theories are currently incompatible when it comes to the extreme environments found near black holes, where both gravitational forces and quantum effects are significant. This dissonance between the two frameworks is one of the primary challenges physicists face when trying to develop a theory of quantum gravity, which would unify these two perspectives into a single, coherent model. Moreover, black holes might also hold the key to understanding the origins of the universe itself. Some theories suggest that the intense conditions near black hole singularities could provide a way to study the very birth of spacetime. Additionally, if wormholes do exist, as suggested by some interpretations of quantum gravity, they could potentially offer a mechanism for traversing vast regions of spacetime. While such travel remains speculative, these ideas encourage new lines of inquiry that could one day lead to a deeper understanding of the fundamental workings of the universe.